All right. Good afternoon, morning, night. We are in gravitational electric fields, so the remaining two objectives or sub-objectives in objective 1 and objective 2. So we are going to finally check off our draw gravitational field lines for uniform fields and for point masses, and draw electric fields for protons, electrons, parallel plates, and combination of charges. That's what we're doing today. And let's begin there. So starting with the review of gravitational and electrical forces. Gravitational forces are created and experienced by masses using universal law of gravitation. The units are in newtons, and one thing that's important is they're always attractive, which we have decided to call negative. Even though it doesn't show up in the equation, we have to think of the gravitational force and fields as always negative because it's always attractive. The electric force, which is created and experienced by positive and negative charges using Coulomb's law equation, creates positive or negative forces. Those positive forces are repelling forces, whereas the negative forces are attracting forces. When we look at fields, the field is a force a mass or charge would feel at a given point. So it's not dependent on the mass or charge that is placed there, which we call a test mass. It's dependent on just the position in a field or some distance away from some other mass, as shown by these equations, right? A gm over r squared because it's dependent on that mass, or kq over r squared because it's dependent on the charge, and of course the distance. We're going to focus on the units, where newtons per kilogram is for gravitational field, newtons per coulomb is for charge. And this is going to help us with identifying how do we make sense of these field lines, because the field lines are really just visual representations of possible force vectors. And since it's per unit kilogram or per unit charge, really we're acting as if we were placing a 1 kilogram mass or a 1 coulomb charge in that position. As we look at point masses and point charges, there are some rules to go with this. But really, I want you to, before we move forward, is think about this as, what if I were to place some mass right here? And of course it's positive because all masses are positive. What force would it feel? Well, it would feel an attractive force. Well, what if you placed a positive charge over here? Would it feel an attractive or repelling? Well, it would feel a repelling force. What if I placed a positive charge right here? Would it feel a attractive or repelling force? Well, positive and negative, so it would feel an attractive force. And by imagining if we were to place a positive charge anywhere in the vicinity of these charges or multiple charges, we can start thinking about how we would draw field lines. So we're going to start by doing an activity using the support document, charges and fields field mapping. In your document, in your support document, which is linked in our slides, linked in this video description, this charges and fields PhET will take you to the PhET activity that I want you to be on. A lot of this I want you to be doing ahead of me. So please, I would say every time we start a new part, I would like you to do that on your own and come back and check to make sure that everything kind of matched. And if you have any questions, hopefully I'll address them. So the beginning observations, I want you to first start opening up this PhET. This PhET's going to look like this, where you can move a positive charge onto the screen, a negative charge onto the screen, and then there's a sensor, which is the yellow sensor, which will kind of show you the fields. These are field sensors. And these arrows are all field lines. So positive charges add on, and then you'll see different field lines. If I get rid of the electric field, it's not existing. If I show it, it's there. I want you to do click direction only, so we don't worry about these shaded versions of the electric field, because we draw them the same. And we're going to talk about how to show how electric fields are stronger or not as strong with our diagrams. Don't worry about voltage. Don't worry about values. Grid, if you'd like. But really the focus is these charges. So let me reset. We have this black screen. And our first beginning observation says, open the charges of PhET, and what can you change about the simulation? So we can change the charges, right? Positive or negative, sensors, and whether to view electric field or not. And that's what we're going to focus on. When you put the sensor on, let's do direction only. When you put the sensor on this, it shows you the direction and magnitude of the E field. Right? So the electric field should be stronger when closer, weaker when further away. And its next question is, how can you make a charge of positive 2 nanocoulombs or negative 3 nanocoulombs? And so I'm going to give you that trick. You can just pile them up. So now that has twice the arrow, right? Twice the field. If I move it off, it's going to be twice the field. If I want to put in negative 3, I just put 3 on top of each other. And you can see it getting stronger and stronger, both in the directions and also in this E-field sensor. So you can just pile up positive or negative charges. All right, let's move on to part 1. So remember, you can do this on your own and then check your work later. I'll be asking you to place 4 positive nanocoulomb charges at the same point and copy pasting a screenshot. And then separately, kind of resetting the simulation, doing negative 2, so 2 electron or 2 negative nanocoulomb charges and put it at the same point, and then pasting the screenshot. Make sure you include E-field sensors in there too, because it's going to show us the value and what happens in magnitude and direction for each of them. So I would go to my own sensor. I'm just going to show you what I'd like you to do and put 2, 3, 4 in the same point, and then drop a sensor somewhere. I kind of want to see the value of that sensor, so I might set it somewhere within the screen that I can post it in. So yeah, I'm going to do it right there, and then I'm going to take a screenshot. All right, here we have it. You can see the difference between these two just by looking at it is the direction, but when you look at the E-field sensors, you can see that the positive 4 nanocoulomb charge has a larger E-field than the negative 2 nanocoulomb charge, and I tried to place the E-field sensor at the relatively same distance away. Now, how do we actually show this in a picture? And we're going to show that later, but this would be shown by drawing more E-field lines coming out. Now, E-field lines are always symmetric. And so, whereas this one might have, 1, 2, 3, 4, 5, 6, 7, 8 E-field lines, maybe this one has less. And so there's less density. So it'd be like 1, 2, 3, 4. And that should be symmetric. But let's see, this is the one that's not symmetric. Going there. You can see the density shows how strong the field is. We're going to talk about that later too. All right, the next up is complete the diagrams and copy paste the image of the field lines below. We're going to do 2 equal opposite point charges and 2 equal like point charges. And this is one where I want you to put an E-field sensor on there, but I want you to move the E-field sensor around while you're doing it. So go ahead and when it says put them in, I want you to put them in a line. So I want you to actually put a positive and then a negative like this. And then this one be maybe 2 positives or 2 negatives. Okay. I'll pause the video. I want you to complete this. All right, here we go. On the left, where we have positive and negative charges, you can kind of see that the electric field lines are pushing out of the positive charge, but being attracted to the negative charge. And if I were to draw these, I can definitely see there's a line right here. And we kind of want to make this symmetrical because it's going to happen on both sides. I see a line kind of passing through right here. And similarly, on the opposite side, symmetry, boom. And if I were to go outward, like facing away, I see one coming in, but I can see it kind of coming back in. And that does happen. It goes back out and it comes back in. And then even way back out here, it might kind of shoot out. But maybe at some point in time, it might come all the way back into this negative charge right here. And you can see where the strength of the electric field lines are more, right, more density, there's stronger electric field. So you can see how the density on the outside is less on the right side and the left side, but the inside is a lot stronger. Um, on the other side, there are opposing, and this one might be a little harder to draw, but one thing I do see is there's this up right here, and there's this down right here. But electric field lines can't be going both up and down, right? They must be going one way. So where did those come from? They come from actually some in right here, and then it pushes up. And actually, let's make that a little better. It kind of stays on the left side. And then these are going to go in as well, and then push up. And so they kind of stay separate. Right here. And then same right here, kind of push out, push out, push out. On the opposite side, it has the same type of pattern. And again, what are these field lines representing? They're representing the force acting on a positive charge if they were placed right there. And so instead of doing this superposition mathematical principle where you're adding the sum of the two forces depending on the distances, and then it gets over complex because of the different angles that it's being acted on, we draw these field lines to make this easier. And there's even one back here going straight back. Okay. So that may look weird, but we're going to come back to this later. Now we have some questions. When you have two like charges, where is the electric field the greatest? Is there ever a point where the field will be zero? When you have two opposite charges in a line, where is the electric field the greatest? Is there even ever a point where the field will be zero? And compare the electric field lines of two equal positive charges and two equal negative charges. Outline the similarities and the differences. So in order to answer 7 and 8, you're going to need to use the E-field sensor. So if you played around with the E-field sensor, I think you might know. I think I still have one E-field sensor playground available. And so as I go around, it's really small on the outsides. But if I get close to the insides, and it's with positive, of course there's a 0, right? It must be somewhere right in between. And then where is the E-field the strongest? Closest to the positive charges. I'm going to pause this and do the positive negative as well. All right, here's my positive and my negative. So as I go around, it kind of follows the same pattern, but you can see how it's attracting towards the negative, but repelling from the positive. What about in the middle? Unlike where you had two like charges, there is no 0 point, and of course the strength is the strongest closest to each one. So where's the electric field the greatest? Closest to the charges. Is there ever a point where there will be 0? No. Or technically infinitely far away, maybe? But yeah, infinitely far away, but inside the screen, no. Compare the electric field lines of two equal positive charges and two equal negative charges. Outline the similarities and difference. I'll allow you that's for you. You do it. And then there's more complex scenarios. And I want you to come up with these complex scenarios. Include 3 field sensors in each of your scenarios below. And I want you to kind of play around. Also in part 4, play around. I would think this is very important. I want you to do this. I want you to make a line of negative charges close together, but equally spaced apart. I want you to describe how the field looks above or below the line, and I want you to imagine if this line continued infinitely, so it's just this long line of negative charges, how would the field lines be drawn above the line? And after that, part C, place another line of equally spaced positive charges some distance away from it, and I want you to imagine what's happening inside of that. These are called parallel plates. So before we move forward, I want you to pause the video and make these two and complete this worksheet because it's going to be super valuable. All right, and we're back to this document where we're going to draw our field lines. So as we look around this mass, I imagine what direction would each point mass feel, or small mass feel, and it would feel an attractive force from all directions. So we have radially outward lines, but inward facing arrows, showing that's the direction of a force that a mass would feel. For a point charge, well, we've already kind of imagined if we put a positive charge next to it, if we placed a positive charge anywhere around this, it would feel a repelling electric field. Ooh. And for a negative point charge, if we placed a positive charge anywhere, it would feel an attractive force. One thing you might have noticed using the activity is some of these rules occurring. One is that all of the fields are perpendicular to the surface. That's because the force in the field is the strongest near the surface, and so it's going to be pulled radially inward once you get that close. They also never cross. You can't have two different forces being felt at one point in time from the same source. So they must also always be drawn in a way that they either get very close together or get further apart, obviously. The concentration shows the strength, as we saw in the activity with the positive 4 nanocoulomb and the negative 2 nanocoulomb. Of course, in this picture, I drew them all with equal magnitude. And of course, the direction is important. So those are our 4 rules that we'll need to know. Now, when we move forward and we look at the 2 masses and 2 charges, and these are considered non-uniform, meaning we're looking in space, we're looking in at the micro level, they're non-uniform fields, meaning they are changing if you move some distance away. We're going to look at 2 positive charges. We're going to look at 2 negative charges. You'll see my masses are next to that as well. And then I look at opposing charges. So we have just seen, I believe, 2 positive charges where we have, and I draw it in blue, they kind of come close, but they never cross. And they just push away. And then they'll always, and you want to think of when you put a positive charge near any of this, is it going to attract to one or the other? No, it's always going to be pulling away. So those are all arrows pushing away. And even imagine you plop it in the middle of these 2 positive charges. There is a central point in which you would feel 0 force, but once it moves any bit away from that, it's going to be pushed either upward or downward. We have So I'm going to pause this video. I want you to try to do both these masses, the negative charges. You can use the support from the PhET lab if you'd like, and then I'll reset. All right, so I finished drawing the lines. I haven't put in the arrows, and you notice that they look relatively similar to the 2 positive charges, except where the positive charges are pushing things away, these negative charges are attracting positive charges. So they would follow a same path, except instead of repelling, they would be attracted to these. But once it gets into the middle, it might want to join one or the other. Similar to masses, it's also attractive. So all masses will feel this field. Remember, if you place an object right here, which direction will it go? Well, it's going to go towards the mass. It might feel a pull towards the left and right, but if it's closer to one or the other, it's going to feel that force. And lastly, we just drew these earlier. We have a direct line in the middle, and we have some outside lines. Most importantly is all of these should be symmetric. I might not do the best job at making them symmetric, and I might not do the best job at making sure that they hit perpendicular, but you want to just do your best. Now they are attracted to the negative, so I'm going to draw arrows towards the negative. and if repelling from the positive. All right, so those are our point charges. These are all non-uniform field lines. And this is everything we've done in that field mapping activity. Though not all fields are non-uniform, and actually the simpler ones are uniform. And this is what we're more used to, going back to like mechanics and Unit 1. When we were near Earth, where our gravitational field strength is 9.8 everywhere, we have, actually let's do this, down arrows attracting to Earth. And technically, this line shouldn't end, right? I mean, it does curve a little bit, but we cannot observe that. And so we're kind of semi-zoomed in, where we have a uniform gravitational field, and that is 9.81 newtons per kilogram. That means these should be equidistant because we have a constant field strength. When you make these parallel plates with positive and negative charges, when you're in the middle, you might notice that you have uniform fields. But once you get to the ends, you get these edge effects. And these also should be, I didn't do a great job, they also should be equidistant inside. But these should have these edge effects because nothing is infinite. So there's always going to be this edge to these parallel plates. Whereas the Earth, even though it is round, it's so large that no matter what we zoom in, it kind of looks flat, and that's what throws some people off. And they should all push downward towards the negative charges. So when we zoom in on the gravitational field, and we go over and zoom in on the electric field inside of a parallel plate, these look similar to us. And that helps us in certain experiments in which we want to shoot something through these parallel plates. But we're going to get to that when we look at kind of the math of this. So right now, all we need to do is identify how field lines are drawn in uniform fields, such as these. These are the only two that you'll be working with in uniform, near a planet or inside of a parallel plate, and non-uniform when you have point charges all around. All right, that sums it up. I will see you in class.